Okay, so we have, like we said, been in an ice age for the last million, million or so years in an intense one. Um, a few more million before that, but back here, 8 to 10, million years ago, we were not. And so the next question is kind of why, and what do these high amplitude variations in the modern, or the more modern record reflect? They're very high amplitude, very regular variability there, but we don't have that kind of variability up here. And really, what the amplitude there reflects is that we're in an ice age, and so that there's permanent ice cover on the Earth's surface, right? During this period here. Um, Back here, when the Earth was much warmer, there was not permanent ice cover, and so you couldn't leverage the isotopic ratio of the ocean to the same degree because it really requires the persistence of ice cover. Okay, and so these large amplitude fluctuations reflect glacial interglacial cycles is the terminology that we use, um, and the question there's a couple of questions here. One, they differ in timescales, right? One is what drives glacial interglacial variability. Another is why are we in a glacial period now at all, and we weren't, 4 million years ago? What's driving that time scale of variability, right? And so reconstructing a climate record is you can do it at a number of very large range of scales. We talked about annual variability in CO2 levels. Then we talked about how it's changed over 1,000 years, a few thousand years, then a few hundreds of thousands of years, and now over very long time scales. But what we discussed next was zooming in on those glacial interglacial timescales. And what we said is that the record, if you look at the periodicity, this is a very busy figure. You guys don't need to know this that thoroughly. Not this one anyway, but you definitely need to understand this stuff. And so you can see that these have regular periods to them, right? This is CO2, and this is temperature. Excuse me. This is temperature. And so the question is, what's driving that cyclicity or periodicity? And the answer is that the orbital parameters of Earth, the way that Earth orbits around the sun, changes in periodic ways. And we said that this is really similar to if you take a top and spin it, a spinning top. As it slows down, it starts to kind of wobble like this, right? And what happens as a result is that the actual axis that we rotate on changes in its angle, and it also does this thing called a precession, where it kind of moves around in a circle. Okay, and it does those two things with very characteristic timescales. The precession takes about 23,000 years, 25,000 years, something around there. The tilt wobbles at about 40,000 years back and forth, and it moves several degrees. I think about 4 degrees back and forth. And the actual eccentricity, we would say, is a term for that. That how circular or elliptical the orbit of the Earth around the sun is changes as well. Okay, and so that period is about 100,000 years, but embedded within this, there's actually another period that's about 400,000 years. I think that has to do with the orbit of Jupiter primarily, and how that affects Earth's orbit. But nonetheless, regardless of the reason, these things do change, and they change in periodic, predictable ways. And they have predictable implications for the Earth's climate system, right? Because everything comes back to the amount of radiation, the amount of energy we're receiving from the sun. And so if that changes fundamentally, then that's going to fundamentally change the distribution of the energy on our surface and the global average temperature as a result, or at least the average influx of of energy. How it's processed in the Earth system is kind of up to the Earth, right? And so if we compare that to these records, what you'll find is that these records have a very clear 100,000 year signal generally, or it's about 100,000 years. And if we look at the longer record, it might be better. Where's that one? Here's another one. It's got these periods of about 100,000 years. Within that, there's another periodicity, right? This kind of, my mouse is in the wrong place. So there's a couple of periods, right? You can see these ones very obviously, but superimposed on that, there's this smaller amplitude, second order variability, and that all relates back to these orbital parameters, the so-called Milankovitch cycles, named for this gentleman here, Milankovitch. And so as a result of these things varying, the amount of, we say, solar insolation, the amount of energy that we receive varies. And that's what I'm showing, this figure shows here, right? The yellow one, the yellow panel is the radiation balance, and that's just the solar flux at 65 degrees north in units of energy, watts per meter squared, right? And that varies. It varies as a result of the combination of these three factors: the eccentricity that has this, 100,000, 400,000 year period, the obliquity, which is how tilted the axis is. It has about a 40,000 year period, and the precession, which again is the axis actually like wobbling around in a circle. Okay, and that has a period of around 23,000 years. And so all of those waves, really those waves combined, they add up or sum to produce this. And if you compare this to the record of ice ages or global temperature, you will find that in general, the ice ages seem to line up, or the glacial maximum seem to line up with when the variability is low amplitude. Okay, that was the point that we made. The higher amplitude fluctuations seem to line up with warm periods. Okay, cold times seem to line up with times of low amplitude variability. Now, the next question is why? Why is that? Okay, and I made things a little bit confusing here, and I did it on purpose, really, because it is confusing, and it's a challenge to understand this. And unless you really think it through, it's hard to intuitively see how the climate system works. It's really complex, and there are lots and lots of feedbacks. But what we decided, or what I posed, the question I posed to you, was if orbital variability is changing the amount of radiation we receive from the sun, and that is driving glacial interglacial cycles, that means that the amount of energy we're getting from the sun per unit, per square meter, is what dictates global average temperature, not CO2 levels. But we've been looking at all of these records of CO2 and temperature, and they line up perfectly. So how does that work? If CO2 and temperature line up perfectly, and temperature is being driven by changes in Earth's orbit, that seems to suggest that changes in temperature are driving changes in CO2. Okay, because CO2 and temperature are inextricably linked. They look just like each other. And temperature, we just decided, because of Milankovitch, has little to do, at least variability in temperature has little to do with CO2. It has to do with orbital parameters on these timescales anyway. So what's the deal, right? That's really the next question, and it just has to do with feedbacks. And so I guess I'll stop this video here and do another one on climate feedbacks real fast. That'll just be a few minutes long, but yeah, that's where we're at.